Hi everyone, welcome back to my channel. In my second video on the 8563A rebuild, I promised I'd do a full teardown of this dead OCXO module you see here, but only if the video hit over 50 likes. Well, you did it. Huge thanks for all the support, likes and comments. It means a lot. So today we're diving deep into this beast. There's a ton to cover. How it works, what's hiding inside, and why it's so critical. So no more talking, let's crack it open. I tried everything to open the box, heat, tools, even a blowtorch, but the base was fully welded to the casing. In the end, I used my Dremel. It took time, but I finally cracked it open. Inside, the oven is packed with insulation foam. I tried to remove it carefully, but it was too brittle, probably from years of heat cycling. There are two boards inside. The first one is the insulated section, which likely houses the oven and oscillator. The second is the control board fixed to the base. They are connected by a flexible ribbon cable. After removing the back side of the oven to see the oscillator board underneath, I connected my power supply to the OCXO port, but without enabling the oscillator since this part is known to be dead. Using my old Flir thermal camera, I watched the temperature climb steadily until it settled at around 60 degrees Celsius or above. That's totally normal for an OCXO. It's supposed to run hot. Let's take a closer look at the entire assembly. One thing stands out. This board is built with discrete components, no integrated circuits here. Next, we have the ribbon cable linking the oscillator board to the control board. On the oscillator side, there is this round shape. That's likely where the crystal sits. And check this out. A transistor is mounted directly to the oven. My guess, it's acting as a heating element pumping heat into the metal block. For sure, this is the first time I've ever seen a transistor used as a heating element. What a surprise! Let's unscrew the control board. Everything is on top. Below, there's only a potentiometer for fine-tuning the oscillation frequency. I'm also detaching the metal block from the oscillator to see what's underneath. And here it is. The thermal paste is completely dried out. Under the metal part we see a crystal, as suspected, marked piezo on top and 10 MHz on the side. So this is our 10 MHz crystal oscillator. I couldn't find information on this specific part, but it's clearly a high precision component. The two wires from the metal plate are likely the thermistor leads, used to monitor and regulate the oven's temperature. To gain a better understanding of the system, I've made a reverse engineering process and developed the following schematic. I provided a link to this schematic in the description. The blue section is the oscillator board, and the purple section is the control board. Let's start with the control board. The 50-volt supply feeds an LM317 regulator configured to output a 10.77 volt, which is an unusual value. The temperature regulation uses an op-amp as a comparator. It compares the voltage from the supply divided by R34 and the thermistor resistive value with a 1.1 volt reference. This comparator manages the heating by using on-off regulation. I measured the thermistor to be around 50 kΩ at 25 degrees Celsius. The transistor, or heating element then, is connected as follows. The collector is directly connected to 15 volt. The emitter is connected to two 3.3 resistors on the control board. The voltage across this load, which should be around 0.6 volt, is forced by Q6 base emitter voltage. The base of the heating transistor is controlled by the Q6 collector, where the heating transistor, together with the Q6 transistor, are forming a stable current control loop, calculated to be around 363 mA. Let's take a quick look now at the oscillator's schematic, which is the part I'm less familiar with. So please don't hesitate to comment if I said something wrong or incorrect. First, there is this LM366 Zener diode, which regulates the oscillator board's voltage to 5 V. This is, I guess, a preamplifier circuit which provides the biasing for the crystal oscillator. This part is presumably the oscillation and amplification circuit which maintains the crystal's oscillation while getting rid of the surrounding frequencies and ensuring the signal is centered around 10 MHz. One of the crystal loads is made with a varactor diode. By changing its reverse DC bias, we change its parallel capacitance. According to the datasheet, a voltage range of 0.4 V to 5 V adjusts its parallel capacitance from 8 pF to 19 pF. This tweaks the crystal's load capacitance, shifting its frequency by a few ppm, around 10 to 20 Hz. This voltage is adjusted via a potentiometer we saw earlier. Next, the preamplified 10 MHz signal goes to the main board, where it is amplified further in a second stage and buffered in a third stage. The final output is directly connected to the SMB coaxial connector, ready to be used externally. Finally, the second op-amp converts the 5 V enable signal into the oscillator board power supply, effectively turning the oscillator board on and off. To get a clearer picture, I simplified the schematic a bit and ran a simulation in ngSpice. Let's start with the oven control first. To model the thermistor's behavior, I used the behavioral resistor starting at 51 kΩ. Its resistance decreases over time, down to 1 kΩ at 100 milliseconds, to mimic how a real thermistor reacts when heated. Let's run the simulation now. I set a 1 millisecond startup time to capture what happens at the power-up. We can ignore this initial ramp-up and focus on the details. The simulation shows that the current almost matches with my earlier calculation of about 363 mA. The heater turns off when the thermistor reaches around 8.5 kΩ. At this point, the heater current drops to 0 mA and the on-off temperature regulation starts. Let's focus on the oscillator board now. I replaced the crystal with its RLC equivalent model tuned for 10 MHz. For simplicity, I removed the varactor diode and replaced it with a fixed 12 pF capacitor. Let's run the simulation now. Here again, I added a short delay to observe the startup behavior and to kick in the oscillation. And there it is, the model for the crystal is oscillating. Let's zoom in for a closer look. The crystal itself oscillates properly, but the amplified output is distorted. I must have missed something in the simulation or in the model. The oscillation period, however, is around 100 nanoseconds, which matches our 10 MHz target. Now let's test what happens without the 5.6 microhenry inductor. Indeed, by testing each component on the oscillator board, I came across this dead inductor, which could explain why the oscillation doesn't start anymore. To confirm this, I replaced the inductor value with a near zero value of femtohenry to simulate its absence. Sure enough, without the inductor in the loop, no oscillation starts. This confirms this part is a culprit. Back to the bench. I took out the faulty 5.6 microhenry inductor and will first check if it's actually broken. Then I try to fix it myself. I suspect that thermal cycling may have broken one of the wires connected to the inductor pad. As expected, measuring the inductor with my LCR meter shows no continuity. It's completely open. After applying some pressure to the chip inductor, the pad popped up, revealing the disconnected wire on the left. Now I'll tin this wire and solder it back onto the PCB for a quick test. My bench is a bit messy, sorry about that. When I press on the inductor to remove the faulty pad, some ferrite powder and plastic spilled out, making this mess. Anyway, I think I managed to apply enough solder to the wire. Let's reattach it to the PCB. There we go. Now let's measure its inductance again. And it works! 5 microhenries. That's slightly lower than expected. Maybe the loss of ferrite powder explains the lower reading? With the inductor back in place, let's test this oscillator again. I've connected the oscillator's output, the SMB connector then, to my frequency meter and my oscilloscope to get a precise frequency reading and be able to see the waveform. I'm also using my thermal camera again to make sure the oven is still working, as I've done some harm to these boards to create that schematic. Let's start by turning on the 15 volt first. I'm checking if the temperature is increasing, and yes, it is. The current is decreasing now as the temperature regulation starts. Let's turn on the 5 volt enable signal and yes, it's oscillating. I can read a perfect 10 MHz with the frequency meter and the amplitude I read on the scope is clean and fine. I'm also interested in measuring the control board voltage and I read 10.41 volt, which is a bit less than the 10.77 volt I calculated earlier, but still within the same range. The final test I want to do is to adjust the potentiometer to find minimum and maximum boundaries of that oscillator. Let's do it now. I've reached the limit of 10 MHz plus 10 Hz. Let's go back to the other direction. I've reached the other hand and I'm measuring 10 MHz minus 9 Hz. So in total we have a trimming capability of about plus or minus 10 ppm for fine adjustment. I'm bringing it back to a perfect 10 MHz now. Measuring the temperature once more, 58 to 59 degrees Celsius. All good. Let's do one final check inside before closing it back up, now that I'm done with this oscillator. Oops, it's still hot. I'll take one last look at the back of the oven and at the control board. And that's it. Let's close it up. By the way, I won't replace the inductor. I leave this OCXO as it is for now. Who knows, we might see it again in the future, since I may need to run some tests with a very precise 10 MHz oscillator. I've reassembled the oscillator and I am running one last test just for fun. Let's see what happens. 10 MHz, plus or minus 1 Hz. Perfect. That wraps up this OCXO teardown video. I hope you enjoyed it. Let me know in the comments if you would like to see more videos like this in the future. In case you didn't, please don't forget to subscribe so you won't miss my next videos. Thanks so much for watching and see you next time. Bye.